Hello everyone and welcome to Arundel, a show where we look at how to implement a modern, well, some might even say postmodern, distributed database, which is quite unusual, which is written in Zig, which doesn't allocate memory, which claims to be extremely reliable and extremely fast. Okay, so let me start with trying to reconnect to my Twitch stream because apparently I am disconnected right now. Okay, seems I am backend. Okay, so what are we going to talk about today? And let me actually share my screen because that's going to be hugely useful. We are going to, as usual, talk about storage, about LSM, about the grid, about all that stuff. And in particular, today we are going to talk about our block allocator, about our FreeSet. So the overall topic is that we are looking at how Target-Beetle's grid evolves over time. And last time we took a very close look at the superblock. And the idea here is that our grid, which is the main storage, which is subdivided into equally sized blocks, stores a sort of persistent data structure. A data structure with a lot of pointers. And the root of that data structure is stored in the so-called superblock. So when you want to mutate something, rather than mutating the data structure in place, you allocate new blocks and you place a second data structure alongside the old one, keeping the pointer to the new root node in memory. And after some time, when you realize that, hey, your new data structure is very large, you go and persist this new root pointer into the new superblock. Okay, I'm not sure if I'm coming through completely right, but well, let's see. Okay, so today we're going to talk about how we allocate these new blocks if we want to write something. And the answer is, well, not as simple as it seems, because it seems that the answer is going to be just a bit set. So we'll maintain a bit set of blocks in memory, and we'll like mark 3 blocks in this bit set, and whenever we want to allocate something, we take it off this bit set, mark it as full there, and that's it. Conversely, when we want to free something, we mark it free in the bit set and allow for reuse. This is not that simple because remember, at any point in time, we can crash. And if we have crashed before we persisted our new if we crash before we persisted our new route to the superblock, so if we crash in this state, we recover starting from this state. And that means that you cannot just free the blocks. So, okay, assume that we started in this state, and then we wrote something here, and then we realize that this block is now free. Now, free. And what if we immediately reuse this block to store some new data structure? So we went and like destructively rewrote whatever blue stuff was in this block before. So there was like some blue stuff before. And while we were processing, we realized that, hey, we no longer need this block because this new tree doesn't use it. And then we freed it, and then we needed to allocate a new block, and then we rewrote it with orange stuff. This is problematic because if we at this point crash and then restart, then what we'll see here is going to be an orange block and not a blue block that was there. So that is like the core trick about the FreeSet. We don't release blocks immediately. We can only free a block once we rolled over a checkpoint. So rather than immediately marking this is now free, we rather say that this will be free in the next checkpoint. And only after we saved our data here, we can actually go and reuse this block, which is very, very abstract. So let's go straight to the code and see how this all actually works, because it's going to be hopefully much simpler and much more concrete. So FreeSet. FreeSet. FreeSet is data structure which allows allocating the blocks. Internally, it stores the actual sorry if I'm going to cough a little bit. I'm still I'm not sick from last week, but I'm still coughing a little bit, so bear with me. Okay, so this is the FreeSet. The core data structure is blocks. This blocks stores the set of blocks which are allocated. And then we have this staging. So staging is the blocks which we are going to free in the next checkpoint. So we kind of like, at the current state, we no longer need the data which is stored in the staging blocks, but we might still need this data if we crash and recover in the previous checkpoint. So only after we recover in the next checkpoint, the staging can be free. And there's going to be there's going to be this like double buffering kind of situation where in the end we roll changes from staging and into the blocks. So let's start looking at this data structure one by one. And I guess, like the two simplest functions we can look at is free and is released. Is free checks if this block is currently marked free, which means that it is not marked allocated. And isReleased checks whether the block is going to be free in the next checkpoint. So it belongs to the stage, which are just super straightforward checks in super straightforward checks and bits, because again, staging, etc., is just like bit set. So just an array of integers allocated. And this is actually a good thing to kind of like, do some napkin math and to compute the disk SRAM amplification. So you see here we have we also have like index block, but it's going to be like smaller, so we'll get to index later. The main thing is that we have like a staging and blocks. So we have 2 bits for each block. And as a reminder, a block is half a megabyte. So that's our write amplification for each 256 kilobytes of disk. We use 1 bit of RAM, which is again pretty decent amplification factors. So kind of like, we do have to keep the FreeSet for the entire disk in memory. Like again, there is no like way around like keeping some map of your entire data file in memory. But if your amplification factor is this high, you actually end up using very little amount of RAM. Okay, so now let's look at the release function. Again, this is very simple. We cannot release disks. We cannot release blocks immediately. So we go and set just the staging bit set. One interesting thing here is addressing. So blocks, like the address of a block U64 is actually always 1 based. So when we want to toggle a bit, we actually go and do this -1 here. Why is that? Well, because one of the principles, well, not principles, but rather like low-level coding guidelines that we have in Tagabitl is that 0 data is embedded. Basically, every time you see something which is 0, in terms of like physically 0, just 0 bytes, you should know that this is not actually a 0 value, but that is an invalid value, and you should crash. And that is because, in low-level programming, it's very easy to get uninitialized memory. It's very easy to get memory which was just like mem-zeroed intentionally. So by forbidding 0 data, we proactively catch any instance where what we're using is actually uninitialized. So that's why we count our blocks from 1. Okay, I see there is a bunch of questions here. With static allocation, does the size of a free bit set impose a maximum size on the grid? So yeah, that's actually excellent question. So yeah, the bit set is statically allocated. So when you initialize the bit set, you pass in the maximum number of blocks this FreeSet could store. And then you allocate this amount of memory. And then if you try to acquire block, and where do we return? Yeah, if we try to acquire block and we run out of blocks, we return null. So yeah, this imposes the limit on the maximum grid size. The cool thing here is that this is purely in memory limit. So if you are running out of space in your FreeSet, you can crash replica, and then you can restart replica with a higher amount of RAM, and then it will go and just proceed fine. This is actually pretty recent. So before that, what we used to have is that we used to have a format time limitation on the size of disk. So when you create a target cluster, you used to say, okay, I don't expect my disk to grow larger than 16 terabytes. And then if your disk happens to grow larger than 16 terabytes, well, game over. You can no longer use a data file. So we got rid of this extension. Now there is like no, there's no like direct physical limitation to the size of the disk which can be addressed by the target. I think you could run out of I think there is some limit smaller than just, U64 address space of blocks, but basically the larger amount of RAM you give to your replica, the larger disk you can have. And you can move a disk from smaller machine to larger machine, and that will work. Actually, let's see how FreeSet is initialized to like trace this parameter. So FreeSet shard count means superblock storage size limit. And what is storage size limit? Yeah, interesting. The storage size limit is actually stored in the superblock, but I bet that this is a runtime parameter. Okay, right. Yeah. So when we create a superblock, we pass the storage size limit, and where this is coming from, super block init storage size limit option storage size limit, and when we open replica in main, storage size limit, data file size, oh no, it's format. Okay, this is storage size limit from the start, and well, yeah, this goes all the way up to the CLI argument. So this storage size limit CLI argument affects the amount of RAM which you might require, but it doesn't affect the actual data on disk. So if you run out of this storage size limit, you can just move the data file to a bigger machine and continue working. Okay. Interesting follow-up question. What happens if I start Tagebiddle with FreeSet size limit that is smaller than the existing physical grid size? Well, I bet that you are going to get an error somewhere. But that's actually okay. This is concerning because I think I wrote this code. Well, not wrote. I touched this most recently, and I actually don't remember what's going to happen in that case. We again could actually take a look here because it's anyway something I wanted to discuss next. So how kind of this FreeSet is stored in memory. It's a bit set, but like obviously at some point we need to like store something on disk, and Where does this happen? Superblock. Trailer. So we have this checkpoint trailer, and it is going to get used here. Okay, right. So like the kind of like how the FreeSet gets into like targetable main memory. It starts in the superblock. The superblock stores FreeSet last block checksum and FreeSet last block address. And that means that actually the FreeSet itself at checkpoint is serialized to disk as a linked list of blocks. So when the replica starts, it reads the superblocks, and in the superblock, it reads the pointer to the first block of the FreeSet, and then it goes and reads the FreeSet block from disk and decodes it. And yeah, okay, so we have like this FreeSet open, which gets an encoded FreeSet. And here, I'll actually it's interesting. Like I don't see any checks here for the total size of the things, the chunks. Okay, yeah, that's interesting. So we definitely should be hitting an error somewhere, and probably it's going to be it's probably going to be even a panic, but well, I cannot really find it right here. Okay, so yeah, maybe we'll find it later today. So to go back to where we were, we learned how we like check whether the block is free, how we check whether the block is released, how to release a block. We kind of like glossed over this procedure of like opening FreeSet. Well, we know that hey, at some form we decode it from the grid, and then it is there. But specifics we'll cover a little bit later. I guess what I want to show is the allocating, the acquisition process. It's the allocation blocks. Allocating blocks is called acquisition, and this is actually okay. There's some lively chat here in Twitch. Okay, yeah, there is a nice chat, but I don't think there is like any questions I've missed so far. Okay, no, actually, there is another good question. So the question is, okay, so targetable devs say that they use static allocations, and yet we are using like dynamic bit set. So what's like if this is dynamic bit set, and why we are calling it static allocation? That's actually like probably it's fair to say that we as targetable developers actually misuse terminology a little bit. So when people say static allocation, what they typically mean is that you have some kind of like really some kind of like data which is allocated in the data segment of your L file. So this is kind of like static allocation where I just say, okay, so I kind of like, I allocate all memory at compile time. This is not what we do at target middle. What we actually do is that we do, let us call this initialization time allocation. So we don't have a compile time known bound on our allocation. The actual amount of RAM we allocate very much depends on CLI argument that we get. And in particular, like, okay, as we've seen today, we parse this storage limit, and storage limit defines the size of a FreeSet we allocate. But the crucial thing here is that we only allocate in this init method. So you see, we take this allocator in the init, then we allocate memory, but after that, we don't use allocator anywhere. So when you try to acquire the block, there is no place where we go and try to grow the bit set, because we don't even have an allocator here, so we cannot, given the Zix API, we cannot physically go and expand the amount of RAM we allocate for FreeSet. This actually, yeah, this is kind of like a cool thing about Zix API, because, well, if you see, does it have some, I think it should have, yeah. Resize, yeah. So for example, there is like API for resizing dynamic bit set, which takes an allocator and like shrinks or grows your bit set. But because we don't pass an allocator here, we don't actually get to call this API. So we only have to stick to non-allocated subset of the bit set API. And that is the meaning of static allocation. It is not that we do all the allocation at compile time. No, we do allocation at runtime. But we do allocation at runtime only during the init. After init finished, if you've managed to allocate enough RAM, you know that Tagabital cannot crash due to out of memory. And I think when we do allocation, we pass something like map populate or some such to make sure that we do really ask Linux kernel to allocate and pin run memory for us. Okay, so acquisition. Acquisition is tricky. So, well, kind of like conceptually, it is very simple, but in implementation, it's tricky. So conceptually, what we want is that we want to just find the lowest bit, which is free, and allocate that block to reduce fragmentation. So we always like try to allocate blocks with the lowest addresses, so that if we kind of like allocated a bunch of stuff and free a bunch of stuff and start allocating more, we kind of like don't leave holes in our data file. But this is made more complicated because of concurrency. So imagine that inside your database, well, we kind of like talked about this, we have like different trees. And different trees obviously like might want to allocate independent blocks. And we actually want this allocation for trees to proceed in parallel. We'll talk more about this when we get to compaction, but basically the idea here is that we have like a bunch of trees and we tell to each tree, hey tree, please try to shrink yourself, try to like compact your data. And then we expect all the trees to do all the required work for compaction concurrently at the same time, so that we spend only as much time as needed for the slowest tree rather than the sum across all the trees. And that means that we actually need support logical concurrency in this FreeSet. Again, this is important. Tribital is single-threaded. So there is no real concurrency, there is no parallelism. Like only a single thread at a time acquires the FreeSet. But there is logical concurrency. So what you might see is that tree 1 allocates, and then tree 2 allocates. And that happens on replica 1. And then, due to some concurrency, due to differences in disk speed, on replica 2, what happens is that these same two allocations happen in different order. And that actually would be pretty terrible, because recall back then when we were talking about this magical property of the grid, that it never fails the write, we said that we rely very strongly on determinism property of the grid, on the fact that the grid is bit for bit identical between different replicas. So if a replica gets a corrupted block on its local disk, it can request different blocks. It can request the same block from a different replica. And this is a problem because, okay, so imagine that in the first state we have like 3 blocks are blocks number 2, 4, and like 8. So for replica 1, the first tree gets 2, and then the second tree gets 4, because, well, we use the strategy where we allocate the earliest block to avoid fragmentation. But then for the second replica, what would actually happen is that this tree gets block 2, and this tree gets block 4. So, like, the data which is stored in block 2 on replica 1 ends up being stored in block 4 on replica 2. And we don't want that. We want to have determinism. So this is where this reservation things comes from. Before you can allocate blocks from disk, you need to reserve blocks. Okay, this is I realize that I have to draw it. Sorry, I'm not sure if you like it more when I like showing some stuff in VS Code or when I'm like drawing Scarlet Drawer. I personally like VS Code more, of course, but well, sometimes you gotta draw. So, like we have this grid. This grid has a bunch of. Okay, let's try to do it smart way and just double, because exponential grow is cool. Okay, so this is our grid. Has a bunch of free blocks, and we have like 2 concurrent processes which need to allocate. And if we just, you know, just try and give to each process like the block, the first block when it's requests, this might be very much indeterministic, because it's like the first execution, but in the second execution, it so happened that like we moved like this one, the right one was faster, so we at first did allocate first blocks, and yeah, so that's kind of nasty. So what we'll do is that we'll ask each of these 2 processes. Well, let's actually color this differently. This one's going to be red, and this one is going to be green. So before they start running concurrently, we'll ask them to reserve a certain number of blocks. And the red one says, okay, I'm going to allocate. I don't know how many blocks I would have to allocate, but that's going to be at most 5. And we'll reserve these first 5 free blocks for the red one. And then the green says, okay, I'm going to allocate at most like 3 blocks. And then we reserve the 3 blocks for the green. So when they start running, the red one is going to get blocks from this allocation, and the green one is going to get blocks from this allocation. And irrespective of the relative order in which green and red one runs, they're going to get the same blocks. So again, if red one runs first and green one runs first, we get this picture. But okay. But if the opposite is true, if the green one runs first, it still allocates the same block. And the red one still allocates this block. So this is kind of like this is like if you understand Tageeh-Biddle's grid reservations, you understand the difference between concurrency and parallelism, because this is very cute piece of code where there is no parallelism whatsoever. This is just a single thread. And there is no even normal concurrency. There is no green threads, no async await. It's just like a single state machine. It's like normal program which does things. But it has logical concurrency. And this logical concurrency might cause physical non-determinism, which we should battle with this deterministic allocation. So, okay. With this high-level picture in mind, let's actually go and understand how this happens. Okay, so reserve. Someone comes to the FreeSet and says, okay, I'm going to start allocating. I don't know how many blocks I will allocate, but I know the upper bound. So I will allocate at most reserve count. So please reserve me a section of the FreeSet which contains at least reserve count blocks. Okay. How we are going to do this? And okay, so this is actually nasty and complicated, because what would naively do is that you just go through your FreeSet from the start and count how many free bits are there until you have counted exactly reserve count. But that's going to be slow. That's going to be linear. So we use a certain index data structure on top of our FreeSet. So what is stored in the index? The index is sort of like compressed bit set. So in blocks we have a bit for each block. In index we have a bit for a bit for a bunch of blocks, and if a certain bunch of blocks are full in blocks, then we set this bit in index. So we can quickly skip through many blocks in index. Let's actually, okay. Where do we, okay, I want to, okay, yeah, so this is kind of how we maintain the structure in the index. When we want to flip a bit in our blocks bit set, we flip a bit, and then we look whether the entire shard is full, and if the entire shard is full, we also flip a bit in the index. So we know that if a bit in the index is set, then a whole bunch of bits in the underlying bit set is also set. Okay, another question. Okay, it's okay. Thanks, Brian, for pointing out to the questions. Are there any plans for multi-threading, or was that a decision based on the integrity of the data? Is there a reason of scope? Yes, this is an excellent question. So I guess the answer is this. The core processing loop, like the core transaction processing, like the core double entry accountant, is definitely going to be single threaded forever, because this is like the core architectural insight on top of which the entire taggable is built upon. And that insight is that if you are processing highly contended transactions, and financial transactions are typically highly contended, then the fastest way you can do this is by running them very, very fast on a single core. Because if you try to parallelize that work, you realize that due to contention, you have to introduce locks. And locks would actually make your work slower than if you do it quickly on a single thread. But in theory, it would be possible to move everything which is not on this main processing loop to a thread pool. And like one thing we actually considered moving to a thread pool was checksum calculation. So when you receive some message from a network, you obviously want to check a checksum, and well, that means that you need to check through like 1 megabyte. And like, for example, if you receive 2 messages at the same time, it might be smart to offload this work to a thread pool. So 2 threads in parallel go and do the checksum. And this is something we are still considering. We might still end up offloading certain CPU work to a background thread pool, but so far we actually didn't need to do this. So far we figured out that actually we can make our checksum calculation fast enough that this is not a bottleneck. So that's kind of like it. The core is going to be single threaded. We might introduce very tactical, very small amount of multi-threading to offload specific CPU heavy operations, but we didn't feel a pressing need to do this already. Okay, so yeah. Thanks again for pointing out the question, because I see there's like a very lively discussion in the chat, and sadly I cannot keep up with it because I also kind of like, want to share something I know. Okay, so let's get back to our index and blocks. I guess at this point it will be useful to understand how this is allocated, just so we understand like how large is the shard. So the shard count is div exact of block counts by shard bits, and the shard bits is shard cache line, a cache line size, and the size of by the size of U8. So cache line size is 64. And we say that the shard is 8 cache lines, so 64 times 8 times 8, so 64 squared, which is 256, I think. 64 squared, 200. Well, yeah, it sounds like this. So yeah, basically for each 256 bits of our actual bit set, we store 1 bit in the index. Okay, so going back to our reservation, we want to find reserve count unset bits in our blocks bit set. If a bit is unset in the blocks, that means that the corresponding bit is unset in the shard in the index. So we go and find the first unset bit in our index, which is going to be 256 times faster. Okay, so we found like the first not fully full shard. Then we compute the start of a block, and then we go and just count this many free bits in our reserved block. So in the end, we what's block base? Oh, block base, set reservation blocks and set reservation blocks. Well, right, yeah. Oh, yeah, actually, okay, it's actually even smarter than that. It seems like we also maintain the last block we have reserved. So when we are finding, well, yeah, okay, this makes sense. We don't, like, again, there might be many concurrent reservations. So not only we need, so finding just reserve count of 3 bits is not enough. We need to find reserve count 3 bits which are not themselves reserved. And that's why we also maintain the latest block which was reserved. And that's why when we find bit, we actually start, so this like start index, we actually start from like this latest block reserved. So okay, we like found the earliest block we need to reserve. Then we have count how many blocks do we need to reserve, and basically reserve this entire set of blocks for our reservation, which is exactly the picture I was showing you here. So kind of like, again, if we are going to have like more reservations, they're going to look like this. They're going to look like continuous subsections of our grid. And again, it's important to remember that like not all of these blocks are guaranteed to be free. So okay, so this one might be filled, this one might be filled, this one might be filled. So there's like some free, some filled, but it's important that the invariant is that each reservation has at least the amount of free blocks that was requested. So after we've got ourselves a reservation, we can go and actually acquire a block. So our reservation remembers the first block where it starts. So as usual, we use the index to identify the first unset block starting from that the start of our reservation. And then we find an actual bit in the blocks bit set, which is unset, so a free block. So okay, we found a block. This block should not be allocated. This block should not be released. And then we mark this block is allocated. We also mark if the corresponding shard becomes full, we also mark it allocated. So find free block in the shard is pretty easy. So we just look at those like 256 bits of a shard and check if they're all unset. Okay. And then we return the address of the block, and the address, again, the address is starting from 1 to avoid zeros, so it's just the block index plus 1. And that seems like it's basically it. Are there any hidden tricks here? Okay, I guess there should be some. Okay. Are we going to mutate reservation somewhere here? Block count. I was. Yeah. Okay. Yeah. This is the core. So the assert I was looking here for here is the assert that we are not allocating more than we have requested, because again, when we reserve things, we pass the upper bound, and then when we acquire a single block, we need to make sure that we do not actually exceed this upper bound, because that would be unsound in all kinds of ways. And this is a chart that does this. So we check that the block which we have acquired actually fits in the limits imposed by reservation. Okay. So let's see, did we cover everything? Well, I guess, okay, yeah. 4 reservations. Like another important bit is that like concurrency is strictly managed. So first you reserve sequentially, then you allocate in parallel, then you start another round of reservations. And it is important that, like, it doesn't happen that you reserve and then you use that reservation much time later. So that's why any acquired reservation must be eventually forfeited. So that we make sure that there are garbage outstanding reservations which might interfere with concurrency. So that's why the FreeSet also maintains reservation count, and it obviously increments this count when we reserve something, it decrements this count when we forfeit something. When we get past 0, we flip our state from reserving and forfeiting, and we check that those are not concurrent, that those like the reservation and forfeiting stages are properly interleaved. Okay, so is there anything super interesting we have here? Okay, there's this. Okay, this going to be extra tricky at how we actually do the checkpoint, at how we actually flip this reserved bit set into the free bit set. But I guess I'm going to punt on that until the next time, because it's tricky and we don't have much time to discuss it today. I guess another thing we want to briefly cover is encoding. Well, actually, yes. Actually, let's do and cover like really quickly in like just 5 minutes encoding and decoding. So again, the high level thing is that in memory, the bit set is just like straightforward bit set. However, if you think about it, this bit set is going to be like highly compressible, because we always okay, important question. Do you have a stream schedule on Discord or something to get notified when I do streams? The stream schedule, I believe, is on Twitch, and it is really stupidly simple. Every Thursday at 5 p.m. UTC, I'm streaming. So 5 p.m. UTC. Oh, okay, let me. What time is now UTC? So it is 6 p.m. UTC now. So I started streaming at 5 p.m. UTC, which is as it is supposed to be. So just join right 1 week later, and I'll be here. If I'm not going to be sick like I was last week. Okay, and okay. So, going back, encoding and decoding. So, in memory, this is just bit set. This bit set is highly compressible, because if you think about it, this our allocation always tries to allocate the earliest block unallocated. So what you are going to see most likely is that, like, I don't know, 1,000,000 blocks are allocated, and then some blocks are free, some blocks are allocated, and like really, really small amount. And then all the rest of the blocks are free. So it would be wasteful to store this bit set in this decompressed representation on disk. So before storing this disk, we compress it into the so-called EWAR encoding. And that's like super super simple encoding scheme for the bit set, which is kind of like, a run length encoding. So if you don't know, a run length encoding is the idea that if you have data like 333, then like 111, then 2, and then 5, 5, 5, 5, 5, 5. So you have data with a lot of repeats. You can actually store this by saying, okay, we have 3, and it repeats 1, 2, 3, 4, 5 times. And then we have 1, which repeats 3 times, and then we have 2, which repeats 1 time, and then we have 5, which repeats 1, 2, 3, 4, 5, 6 times. So this is run length encoding. EWAR is sort of like essentially a run length encoding, but for bit sets. And for bit sets, it's like stupidly simple, because bits are either like zeros or ones. And again, for our bit set, what it's going to look like is like a lot of ones, then like some amount of like randomness where like there are zeros and ones, and then like all zeros. So essentially, like the way we want to compress this bit set is to say just how many ones as a prefix we have, how many zeros as a suffix we have, and then we store like this middle part as is. And that's exactly what EWAR does. So there are like just two kinds of words. There are like, okay, let me see this way. So we have like this bit set. Before we encode it, we split this bit set into 64-bit words. So there is like, we look at our bit set as 64 bits, and then 64 bits, and then 64 bits, etc., etc. Now we classify these chunks of 64 bits in two ways. They are either uniform, which means that they are 64 zeros or 64 ones, or they are non-uniform. And then we do the following thing. For each uniform word, we do run length encoding. And each non-uniform word we store literally. So okay, let's just go and see this. Okay, encode chunk. So we have like our source words. This is our bit set, but it is sliced into U64s. And we encode it into the target words. So we look at a particular word from a source. If this word is literal, meaning that this is not uniform word, meaning that it is not all zeros and it is not all ones, we say, okay, there is nothing to run length encode. There is like 0 uniform words here. Otherwise, we just go through the source words, start from current position, and count the amount of words which are equal to the current word, which is uniform here. So we probably can say assert is uniform here, but well, it's kind of like obvious because it is not literal. Okay, so and they kind of like encoded all those uniform words. After that, we count, after this like run of the uniform words, we count the run of literal words, and then we say, okay, so we have this amount of uniform words, and this first bit says whether it is just zeros or ones, and then we have this amount of literal words. So again, kind of like control word, then uniform words are not actually stored. We store only their quantity, and then we get literal words. So we store this control word, and then again, like as I said, uniform words are not stored, and the literal words are stored literally, so we just memcopy. Conversely, when we decode this thing, source words, we look at the current word, which we know is marker word because the first word is always going to be marker word. Then for uniform word count in this marker, we go and memset like this number of words either to 0 or to 1, and then we go and memcopy literal words. So again, this is kind of like very simple, very stupid scheme for encoding bit sets which have a lot of zeros and a lot of ones, and it kind of like, you know, if you look at this, like this cannot work reasonable. Like you need like 64 zeros in a row and 64 or 64 ones in a row to make this, like, you know, encoding trick work. Even like a single bit would cause you to use a literal word, which actually defeats your compression. But this is exactly the pattern which works for our allocated blocks in the grid, because we always allocate earlier blocks, so we always going to see a chunk of allocated blocks, then a little bit of blocks in the middle, some of which are allocated, some of which are deallocated, and then we're going to see a chunk of deallocated blocks. Okay. Okay, correction bit. So we don't store any like. So this encoding doesn't do like any kind of error correction or any kind of checksumming. The way we store this whole thing, this whole FreeSet, is that we are going to store it in blocks in checksum trailer, which probably we are going to look at a week later. And in that trailer, we include the checksum for the entire thing. So we do have a checksum. And if that checksum is not going to match, then we are going to read this block from some other replica, which is actually like freaking cool. So imagine you are a replica. You start, you read your superblock. Your superblock contains a pointer to blocks encoded in FreeSet. You go and read those blocks encoded in FreeSet. And like, you know, while you're reading FreeSet, you are in a very peculiar situation where you cannot, like, you know, you don't even know which parts of your data file are allocated and which are free. Like you're like completely agnostic as to like what is happening. So okay, you go and like you read this FreeSet, and like, I mean, well, it's like it so happens that you are unlucky. It so happens that, like, you know, there is some bit corruption and your FreeSet like checksum doesn't match. So like, I mean, it looks like it's like complete catastrophe because you don't know which parts of your disk you are even allowed to use. Like, you know, there's like a lot of data, but well, some of it might be garbage, some of it might be useful, and you have no idea because you don't have this FreeSet. But any other replica in the cluster is going to have exactly the same FreeSet as you. So you can go to any of your 6 buddies, well, I guess you are one of them, so to any one of you 5 other buddies and say, hey buddy, please tell me, what is my FreeSet? Which data I have free? And they will give you their FreeSet directly. Like, again, there is no special code there. This is all like encapsulated in just like read block. So this is going like transparently automatically implemented. So you like get this corrupted grid block from them, install it in your grid, decode the FreeSet. The FreeSet is now going to be correct because, well, you check the checksum of the block because you know the checksum, and then you proceed using the data from your own disk. So that's kind of like, you know, a replica can be like completely amnesiac up to the point of not even remembering what it should be remembering, and it still can pretty normally recover in the cluster because they have this very strong invariant that the grid is bit for bit identical between replicas, which is, I guess, again, doesn't make a lot of sense right now, but hopefully in 2 or 3 episodes this will make sense, because we'll take a closer look at how we store the FreeSet in the grid, how we do checkpoint, and how we do repairs, which at some point is like going to be mostly a repeat of what we've already covered. But it's like, again, this is like very useful because the same tricks in TigerBeetle are like applied again and again and again, and like after you see it's like 3 times in a row, it actually dawns on you how it works internally. Okay, so let's slowly wrap up and do a short recap. We were looking today at the FreeSet. The FreeSet is a block allocator. The job of a FreeSet is to say which blocks in the grid are free, and conversely to allow like using these blocks for data structures. This allocator uses a double buffering strategy, which means that if a block is freed, it cannot be immediately reused by some allocation. The block can only be reused in the next checkpoint. This is because you need to account for a possibility of a crash. And if you crash between checkpoints, you start from the previous checkpoint. So until you actually rolled over the checkpoint, you cannot delete any data from a previous checkpoint. You can only mark data for deletion. So that is like one big application of a FreeSet. We have this, instead of just having one bit set blocks, we have blocks and staging. And free blocks go to staging, and at the checkpoint, we fold staging back into blocks. The second complication of the FreeSet is that we want to allow its concurrent usage. We want multiple concurrent processes to be able to use FreeSet simultaneously and allocate their blocks in parallel. At the same time, we want to guarantee that the actual allocation is going to be deterministic, which is a very like hard problem to square. Like it seems like impossible. Like you both want the allocation to be non-deterministic because you want concurrency, and at the same time you want your allocation to be deterministic so that your grid end up being deterministic, so that you could do this block-wise repair. And the way we solve this problem is by splitting block allocation into 2 phases: reservation and acquisition proper. Only acquisition proper runs concurrently. All reservations happen sequentially. And when you reserve blocks, you don't need to like say exactly how many blocks you're going to need. You only need to provide upper bound. So what happens is, like, say two concurrent processes. One process reserves 100 blocks, another reserves like 500 blocks. They get deterministic regions in the data file from which they are allocated. Then they proceed running in parallel and they allocate their blocks. Each allocates blocks from its own reservation, and that's why as long as each process is deterministic, the combined result is deterministic as well. After this allocation phase finished, they forfeit their reservations, and the block become eligible for reservation in the future phases. Which I think pretty much everything and even more than what I planned to cover today. Okay, so that was hugely productive. As usual, thanks a lot for being active in the chat. Thanks a lot for writing the questions. It's like, it's useful to say not what I find interesting, but what you find interesting. And please join me again at 5 p.m. UTC next Thursday, exactly a week from now. And if you happen to miss the Twitch stream live, then no worries. All recording are uploaded to YouTube, and this is exactly what I'm going to do in 5 minutes when the stream finishes. Thank you for joining, and see you in a week. Goodbye.